Hello everyone. In this session, we will discuss the switching characteristics of a BJT. Now, let us start with a simple symbol and structure diagram of a BJT here. As we can see, we have both NP and NPNP transistors being shown here. By the look of it, you can understand a BJT is a 3-terminal, 3-layer, 2-junction, unidirectional current carrying capability device. Whether be it an NPN or PNP, the current direction is only in one direction always. In the last session, we have discussed the static characteristics of the BJT, and we have not taken into consideration the junction capacitances. So, in this particular session, we are going to understand how the BJT behaves in the transient conditions, that is when it is being switched from off to on or off to on to off state. What is the behavior of the BJT and what is the impact of these junction capacitances on the overall switching operation itself. Let us start with the transient model. A forward biased PN junction exhibits two parallel capacitances, a depletion layer capacitance and a diffusion capacitance. On the other hand, a reverse biased PN junction only exhibits depletion capacitance. As I already had said, under steady state conditions, these capacitances do not play any role. However, under transient conditions, they influence the turn on and turn off behavior of the transistor. So here we can see the model of a transistor under transient conditions. Now here CCB is the effective capacitance between the collector to base junction. CBE is the effective capacitance between the base to emitter junction. And similarly, we have RBE is the resistance between base to emitter. Similarly, we have RCE also. Now, the transconductance Gm, we have two models, one with the current gain and the transconductance. The transconductance Gm of a BJT can be defined as the ratio of change in output current, which is the change in collector current, to change in input voltage, which is VBE. Now, these capacitances, the effective capacitances, are dependent on junction voltages and physical construction of the transistor itself. The capacitance CCB that lies between collector to base affects the input capacitance significantly due to the Miller multiplication effect. Finally, the RC is not shown here but that is an internal resistance between the collector to emitter terminals of the BJT, and we also have RBE, the resistance between base to emitter terminals of the BJT. Now, in the next slide, we will look into the switching times or the waveforms of a BJT. Now, as you can see, due to the effect of internal capacitances, the transistor does not turn on instantly. This is the collector current, and a transistor is said to be turned on only when the collector current rises and reaches 0.9 ICS. Okay. As the input voltage VB rises from 0 to V1 and the base current rises correspondingly from 0 to IB1, the collector current does not respond immediately. You can see there is a delay. This delay is also called as delay time, represented by TD, before the collector current rises. This delay is required to charge up the capacitance of the capacitance of the base to emitter junction to the forward bias voltage of VBE, approximately 0.7. After this delay, the collector current starts to rise and it reaches the steady state value of ICS. The rise time TR depends on the time constant determined by the base to emitter junction. The base current normally is more than what is required to saturate the transistor. As a result, the excess minority charge carriers will get stored in the base region of the BJT. The higher the overdrive factor, the greater is the amount of extra charge stored at the base. This extra charge, which is also called as the saturating charge, is proportional to the excess base drive, and the corresponding current at the emitter is given by IE is equals to IB minus IBS. But since IBS and ICS are related by beta, instead of writing IBS, I will write ICS divided by beta. Now, IB is related with IBS with respect to ODF. So, IB is ODF into IBS minus of this, I will substitute it as IBS, is equal to, take the IBS as common, IBS multiplied by ODF minus 1. And finally, the saturating charge itself is given by tau S multiplied by IE. Now, this is also equal to, I am taking IE from equation 1 and substituting. So, tau S into IBS multiplied by ODF minus 1. So, what is tau S here? It is called as the storage time constant of the transistor. Now, coming back to the waveforms here, once the collector current reaches 0.9 ICS, the transistor is now said to be in the on state. So, the representation Tn, what you are looking at here, is to represent the transistor continues to operate as a switch which is in the on condition, right. Now, when I want to turn off the transistor, there is an interesting thing that we have to note here. Please note, BJT is a controlled turn on and uncontrolled turn off device. So, if I make the base voltage 0, it will turn off. However, the author here indicates that, you can look at the waveform does not stop at 0, the base voltage does not stop at 0, it goes to negative. There is a very interesting theory behind this, and let us learn why this is so and so. Right. So, when the input voltage is reversed from plus V1 to minus V2, and the base current also changes to minus IB2, the collector current does not change for a time that is represented by Ts, and we call this time as the storage time. Now, Ts is the time required to remove the saturating charge from the base region. Now, since the base to emitter voltage is still positive with approximately 0.7 volts, the base current reverses its direction due to the change in the polarity of the base voltage from plus V1 to minus V2. Now, the reverse current minus IB2 helps to discharge the base and remove the extra charge from the base. Without minus IB2, the saturating charge has to be removed entirely by recombination only, and the storage time would be longer. Now, that is why I said, by making the voltage VB go negative, the switching speed of the transistor can be improved. Once the extra charge is removed, the base to emitter junction capacitance charges to the input voltage, which is currently minus V2, and the base current slowly reduces to 0. The fall time Tf of the transistor depends on the time constant Tf, which is determined by the capacitance of the reverse biased base to emitter junction. Finally, we talk about the storage charge itself. Let us look at the storage charge here. So, this diagram shows the extra charge stored in the base of a saturated transistor. During turn off, this extra charge is removed first in time Ts, and the charge profile, this is the charge profile, and you can see the charge profile during turn off. We have multiple charge profiles. Now, the charge profile is changed from A to C. During the fall time, however, the charge profile decreases from C to D, and thereby all the extra charge carriers in the base region, which are the saturated charge carriers, are removed. We finally state that the overall turn on time of the transistor is simply the sum of the delay time plus the rise time. Similarly, the total turn off time of the transistor is the sum of storage time plus fall time. So, we will represent the same in terms of equations. So, T on equals to TD plus TR, and T off equals to Ts plus Tf. Right. So that is about the switching characteristics of the BJT. Thank you.